All right, so we'll go ahead and get started here this morning. So a few things, if you haven't already turned in homework, by the end of the day, either to me or online on D2L, so we can go through those. Maybe a couple of quick notes, I think, on there. Probably the biggest one as far as like the quiz for Friday. It's going to be similar to a lot of things you probably saw there, probably like a tiny bit of naming, a little bit of things as far as kind of like predicting spin states, like high spin, low spin, things of that nature, geometry. And probably a tiny bit from some of the electron counting stuff that we see today, although I'll kind of tell like what I'll give to kind of help with that. So it's not like an overwhelming amount of memorization for like one day right before the quiz. But in terms of kind of with that, because I know I had a question earlier as far as like spin states, what are the, like if you're trying to find spin states of things, what are you looking at in kind of what priority order? Yeah, metal is most important, right? What are your quick trends for metals? Yeah, first row, probably, yeah, most likely high spin, unless what kind of things could make a first row metal not be high spin? Strong. Yeah, really, probably a really high oxidation state and yeah, strong field ligands. Like you kind of almost need one or the other, or probably most of the time, both to really make a first row metal be low spin. Otherwise, they're almost always high spin. And then our second and third row metals are, Yeah, pretty much all low spin. There's very few exceptions. Probably the one that is the most common, ruthenium, when it's +2, can make high spin compounds. Ruthenium, it's right under iron. So ruthenium is probably one of the few ones that so if you get low oxidation states and maybe some really weak field ligands, you can make some of those second order metals high spin, but it's pretty rare. If it's a second or third order metal, for anything we see, you can pretty much expect it to probably just be low spin at that point. All right, so we'll use a little bit of that kind of as we go through some things today as well. But what I want to kind of start talking about today is two things. One, a very, very brief introduction to organometallic chemistry and kind of like what things that adds to some of this coordination chemistry we've been talking about. And then talking about what we call this 18 electron rule, which I think was going to kind of put a lot of these things together as far as hopefully being able to talk about compounds and their relative stabilities based on kind of their electron counts and geometries and things that they have. So as far as kind of a quick introduction, if we're going to talk about organometallic chemistry in terms of just what it is, if you hear the term organometallic chemistry, what does that probably mean? What is involved? Yeah, if it's organic, that means it has to involve carbons. And if it's metallic, it's metals. So organometallic chemistry is pretty much all just compounds that have metal-carbon bonds. So as a whole, when we're talking about organometallic chemistry, we're looking at metal-carbon bond containing compounds. And there's something that's a little bit new with some organic compounds that hasn't come up with some of the stuff we've done so far with coordination chemistry. And one of the biggest ones is the fact that when we have pi electron densities in molecules, they have the potential to interact with metals and d orbitals on metals. Right? If we think about like pi systems and where their orbitals are, there's d orbitals that can have the right symmetries to interact with them. We've seen that a little bit just doing kind of some of the different MO things with symmetry, but it's not that uncommon, for instance, to have something even just like this, where you can have ethylene, or ethene in this case, actually coordinate to a metal using basically just that double bond. And you'll see it often drawn like this, but in reality, in terms of kind of orbitals and interactions, what really kind of almost ends up happening here is that you have pi electron density from the actual double bond that can be donated to the metal, but there's also the potential that the metal can donate back some electrons to some of the usually pi star orbitals on the carbons that are making that double bond. If the metal donates electrons back to the carbons in an anti-bonding orbital, what's going to happen to that carbon-carbon bond? Yeah, it actually almost becomes more of a single bond. And in fact, you'll sometimes see this interaction written instead. You might see it shown as this. In terms of what's going on. And these are almost kind of equivalent notations for describing the bonding interactions that are really kind of happening. The metal is interacting with both carbons, and as a result, that carbon-carbon double bond is actually going to be weakened as a result of that. Now, is it going to be weakened to the point that this bond like elongates all the way to like a normal single bond? Probably not fully, but probably close. You will typically see that out of these interactions. And we can actually kind of expand on this. It doesn't have to be just a single double bond. It could happen with a triple bond, or it could happen to a system that has multiple double bonds. So for instance, we could have everyone's favorite common organic molecule, benzene. What's that? That's close enough for what we're going to do. This probably really, you'll see notations for compounds like this. This has delocalized pi electron density in it. You'll sometimes see interactions to metals drawn like that. So if we see a notation like that, what does this indicate? What does this mean? Yeah, the metal's kind of almost sitting, like if you think about where all the electron density is in this pi system, it's kind of all like above or below the ring is where all the pi electron density is. The metal just goes and sits kind of almost in that little pocket. It interacts with kind of, essentially it interacts with all the carbons at the same time. And one of the things that comes up from a naming perspective, this is one new piece of naming that we'll add. It's kind of the only really new piece we'll add for naming for organometallic things for right now, is that we want to indicate how many carbons on an organic ligand are actually interacting with a metal center, because it can sometimes vary. And in fact, with probably what is the single most common organometallic ligand around these days, which is this compound, that's probably the shorthand notation of it. This is C5H5 minus. If you want the actual name of this, this is the cyclopentadienyl anion. That is an extremely common organometallic ligand. In fact, probably maybe not quite true anymore, but probably as recently as 10 years ago, probably 80 to 90% of all organometallic compounds that were published in the literature contained that ligand somewhere. It's just that common and that often used. And so this particular ligand is kind of interesting because I've drawn it up here, kind of like benzene, because really this is an aromatic system. It actually is an aromatic 6-pi electron system. So it can behave similar to benzene. It just has a negative charge, which means interaction to a metal is actually likely to be even stronger if that metal is a cation, because you have an actual full charge now to help kind of facilitate that interaction. And so it can also interact with the metal in a similar way where the metal can kind of sit in the pocket of the pi electron density. But the cyclopentadienyl ligand has some other kind of ways to interact with metals. And so I'm going to show these as well. So that cyclopentadienyl ligand that I drew initially is kind of aromatic. We could also think of it as having resonance only to the first 3 carbons, and then an actual double bond in kind of the back 2 carbons. And you can have a metal that interacts with only the first 3 carbons and not the back 2. Or for instance, we could have one more variation where we can actually have double bonds here that are just real double bonds, and then the metal bonds to that front carbon like this. So all 3 of these kind of notations mean something different in terms of how the metal is interacting with that particular ligand, which means from a naming perspective, we have to be able to differentiate between those kinds of interactions. And so the terminology we use to kind of indicate how many carbons of a system like this actually are interacting with the metal is something called hapticity. Is that a term that anyone has ever heard before? And so hapticity is basically the number of carbons attached to the metal from a system that has multiple carbons in a pi system of some sort. And it's most commonly used for kind of organic pi systems like like the cyclopentadienyl ligand. And so the notation that we typically see for this is going to be the Greek letter eta, and then it's going to get a superscript for the number of carbons that are actually attached to the metal. So this first one, say right here, where that metal is only attached to a single carbon in that ligand, we would refer to this as eta 1. And this cyclopentadienyl ligand here, probably most of the time, you're not even going to see it written out. You probably just see it abbreviated CP. It's actually the reason why copernicium on the periodic table, element 112, is CN and not CP, is because CP is used so frequently as an abbreviation for this ligand in chemistry that if you see CP, it means the cyclopentadienyl ligand, this 5-membered kind of negative charge delocalized ring. And so notation-wise, we can see it written like this in terms of a formula. Or if we were actually writing the name, we could say this would be, and the way we refer to this is eta 1, and then we could say the cyclopentadienyl, and then kind of that's the ligand component of the name. We're not going to have to change that to an O ending. It actually stays as it is, as the anion in this case. So organic ligands keep their normal name, whatever they actually are. In this case, if it's an organic anion, that's when they're getting that eel ending typically. That's why we kind of see that there. And then if we have, say, this situation where the metal's interacting with the first 3 carbons instead of eta 1, it simply becomes eta 3. Or if we have kind of the top situation, the very first one that I showed, with the metal interacting to kind of the center of that ring, careful, If we're looking at the right one up there at the top, yeah, A to 5 would be the other possibility. Right, so we can have like A to 1, A to 3, A to 5 for cyclopentadienyl. Yes, for the benzene, we could actually say A to 6 to indicate its interaction. Although for benzene to interact with the metal, it's probably always A to 6, so you might not see that notation for it all the time. And in all honesty, benzene doesn't interact with metals often enough in compounds that we're probably going to see that notation really show up for it very often. Yes. Yes, it is because of the negative charge. So what happens, and we'll actually, anyone that does the ferrocene lab in the spring will actually do the chemistry for this. The compound you start with is this with 2 hydrogens, right? And there are hydrogens on each of the other carbons still here, or single hydrogen on each of them. And we're basically going to take one of these protons off. So if I remove that proton, this now becomes a carbon that effectively has kind of a lone pair on it. And if it's got that lone pair, yeah, now we have, if you think back to like how nitrogen interacts with like aromatic systems and stuff in the past, organic chemistry, there are actually these 2 electrons plus the 4 from the 2 double bonds that are the pi electrons now, making a 6 pi electron system. And so it really is like once you've deprotonated it and it has this negative charge, it really is effectively, I don't know if I can draw anything that resembles a 5-membered ring. It is basically a 5-membered benzene that has a negative charge, or a 5-carbon benzene with a negative charge in terms of how it behaves. All right, now, one other thing before I and I'm not going to do too much more, I think naming-wise here, I think that's really all we're kind of showing here, all I really want to show from this. When I'm looking at kind of the different hapticity possibilities, though, are there any ways that I could actually, characterization-wise, try to figure that information out? Of whether it's like A to 1 or A to 3 or A to 5 in terms of interactions? Are there any thoughts or ideas to that? Yeah, bond length is probably the best. The problem with that is if I want to know bond lengths, what do I have to probably get? Bond lengths usually require probably IR is probably not, unfortunately, the greatest for that stuff. It's probably a crystal structure, an X-ray crystal structure. How easy is it to get X-ray crystal structures of things? Yeah, it means you have to grow really nice, pretty crystals that are big enough to get a crystal structure off of. Sometimes that's easy. Sometimes it's really, really, really hard. And so, yeah, there's all sorts of tricks you can try. That doesn't necessarily mean it's going to work. And so sometimes if you don't have access to crystal structure, what are some other ways we might be able to try and figure out bond length information or even just symmetry information for these things? Yeah, NMR is probably another one. The only thing with NMR is then we do have one issue of, are we going to do it on the solid or in solution? Which makes things sometimes weird. Because what happens is in the solid state, if we have something that's like A to 3 like this, if we do solid state NMR, we will see different signals for basically these back 2 carbons compared to the first 3. And we will be able to see a difference like in a carbon NMR in the solid state. But if we do it in solution, they will probably all show up the same because you'll have what's called fluxionality where this thing can kind of spin around. And so the metal might interact with these 3 carbons for now, but in solution, in a few seconds later, it might interact with these 3 carbons instead. And so you'll have some kind of like possibility as far as the movement of the actual pieces of the molecule in solution that you don't get in the solid state that can complicate that. And when you think about doing NMR, if we're doing NMR upstairs, it's pretty much always in solution. And so it does make things sometimes hard to identify some of the hapticity information for these things without a crystal structure, maybe solid state NMR, or some other ways to try and characterize that interaction. So ways we can try and predict hapticity are going to be then the next part of this that we can actually get to, which is going to involve electron counting for things. Right? And so the next piece of kind of all the stuff we've been kind of building towards for this, and this applies to coordination compounds, as well as talking about organometallic compounds, is we want to talk about something called the 18 electron rule as it pertains to transition metal compounds. So when we're talking about the 18 electron rule, first off, where would this possibly come from? Yeah, if you think back to kind of like, if you want to take kind of the most Gen Chem explanation possible, like we had the octet rule for all the Lewis structures in Gen Chem, which was the S and P orbitals being full. Well, now if we have transition metals that have d orbitals, you can take 10 electrons to fill those, 10 more is 18, right? So we're filling the S, D, and P orbitals. Right, so that's kind of, I think, the quick view perspective of this. However, it's kind of, as you see with most upper level things, it's not always quite that easy, right? There's kind of some other perspectives on this too, because the electron counting only actually works for certain kind of geometry preferences, I think, as well. So I want to talk about kind of some of those pieces, and then we'll talk about the actual counting process and how it works. So in general, 18 electron compounds, oops, right, usually offer high stability. If they are octahedral. And I'll also put in parentheses here tetrahedral at times as well. But we're going to talk about kind of some of the limitations of this. So octahedral in particular fits really, really well for this 18 electron rule. And it actually has to do with the MO things that we were talking about previously. So for instance, and I'm going to show one of these MO diagrams quick from the past. So if I'm looking at this MO diagram, and it might be a little bit small, here is kind of my frontier orbital, the set of 3, my T set, and then my E set that's up above. But then I have, if I look, I have 12 electrons in kind of all these molecular orbitals that were way down in energy that were all kind of bonding. If I look here, if I fill my T set, that takes 6 electrons. Well, 12 plus 6 is 18. But remember, this E set that was part of that frontier set of orbitals from the metal is an anti-bonding orbital in an octahedral geometry. So not putting electrons into an anti-bonding orbital, probably better in terms of overall stability or bond strengths that you can actually get. So octahedral compounds, 18 is also a magic number because it basically maximizes the number of electrons in bonding orbitals for things. So that's one of the patterns that we can see for them, and also why 18 electrons is a sweet spot, not just for kind of like SPD electron orbital like totals, but octahedral systems in particular, especially if this T set you see in this image is shown as bonding. That only happens if the ligands are pi acceptors. And that's what we actually see up there. There's the pi acceptor ligand, or basically pi acceptor orbitals on the ligands, which make this bonding. We get an anti-bonding that's not higher up. But in general, large delta O gaps, which means low spin compounds, 18 electrons is the sweet spot for octahedral systems. So all second, third row metals, if it's octahedral, if it's 18 electrons, it gets kind of this extra bonus stability. Kind of like almost when you think about like electron configurations, like way back in Gen Chem, how we said that like for d orbitals, things like to be like d5 or d10, and even shuffle an s electron around to try and accommodate that. Like for compounds, 18 is the sweet spot for octahedral. That's going to be where things are the most stable. Yes. So for things that are high spin, what ends up happening, and generally for it to be high spin, this or set of T set right here probably isn't going to be bonding. It's either going to be non-bonding or maybe even slightly anti-bonding if you have pi donor ligands instead of pi acceptors. In that case, yes, less than 18 electrons actually can still be stable for them. In general, kind of normal trends, those compounds will not be as stable as just kind of normal 18 electron, I think, octahedral complexes. 18 is still going to be the preferred total for almost any octahedral system. But things can be reasonably stable below 18 electrons if they do have kind of like pi donor ligands, or we'll talk about other things that'll make like that delta gap smaller. Does that answer? Did you have a second question? Oh, sorry, go ahead.
If it's tetrahedral, we'll switch. Does tetrahedral go for 16?
Well, let's see if I have, I don't think I have an image of that one. So for tetrahedral, these orders switch, but how many electrons do you have down here? Instead of 12, you only have 8. So tetrahedral 18 is still kind of a magic number because you have 8 down here and then 10 to fill all of your d orbitals. And that'll actually end up kind of still being a sweet spot for tetrahedral. That said, tetrahedral probably has more exceptions than octahedral, and that's actually what I want to look at next. I'll actually use these slides to kind of show this. So In terms of our general kind of trends and exceptions for 18 electron rule, especially for octahedral, works best for octahedral compounds that have large delta O's. That's where we kind of see, like, if something's 18 electrons, an octahedral, it's stable. That will kind of always be the general case for us. And it's extra so for anything that has a large delta O, which if it has a large delta O, what does that mean about that compound? In terms of like spin state things from like the homework? Yeah, low spin, right? Large delta O's are low spin compounds. So low spin compounds, octahedral, 18 is that magic number we're aiming for most of the time. And I do put up here, means it is best with typically pi acceptor or strong sigma donor ligands or strong field ligands in general. It's like carbonyl, cyanides, things like that. Now, when can we get deviations from this? So if we have weak field ligands, there's a couple of things that can actually happen with this. Weak field ligands make delta O smaller. And I'll actually get to the image part that's in the bottom here. If this delta O shrinks, one of the impacts of this is if this anti-bonding EG star is lowered at all in energy, or at least closer to the T2G, you actually make it easier to put electrons in that anti-bonding orbital, which means that electron counts over 18 can start to be a little more stable. That doesn't mean they're going to be preferred over an 18 electron setup, but it does make them more possible to have a stable compound that's not 18 electrons. Likewise, we can also have a situation where if we get pi donor ligands do make this T2G here become anti-bonding, so it goes up as well, which means we don't even really want electrons here, which means you kind of only want your 12 electrons in the bonding orbitals down here. So you actually stabilize low electron counts by having pi donor ligands. So weak field ligands that aren't pi donor can potentially make higher than 18 electrons okay. And likewise, pi donor ligands can make under 18 electrons okay. That said, neither of those will ever be as stable as just an actual 18 electron complex for something that's octahedral. Right. Other geometries, and I'm actually going to back up one slide here. So I'm going to skip this quick. For this one, square planar. This is the MO diagram for square planar. So the important part here is the frontier orbitals is kind of this set right here in the middle, right? So looking from, let me actually, no, that's not what I want. So if I'm looking at kind of this middle 5 sets of orbitals right here, remember, it's this really highest frontier orbital from the d orbitals that we just don't want electrons in. If I don't want to fill that, there's 8 electrons already then from the metal, and I have 8 electrons below from basically 4 different things that can donate 2 electrons to the metal. That's 16. So square planar compounds actually prefer 16 electrons instead of 18. And that will pretty much always be the case. So if you have something that is a 16 electron compound and it's 4 coordinate, it's probably going to prefer square planar. Pretty much all of our late transition metals, and I think I have this in the next slide here as well. Go to this one. Yeah. So things that are square planar, typically always going to prefer 16 electrons. It's most common for second and third row transition metals, especially the late ones. And when I say late, is everyone familiar with what that term refers to? If it's a late transition metal, what does that mean? Yeah, it's like the right side, like over kind of like where nickel, copper, and kind of those elements are and down. Those are the late transition metals. The early ones are over by like titanium, vanadium, kind of the front part of the D block. And so late transition metals, especially second and third row, pretty much always square planar for 4 coordinate systems because low spin. And platinum, palladium, rhodium, iridium, and even gold +3 in some instances, all really like square planar configurations because they can actually make these 16 electron compounds. It's possible to have square planar for like 15 or 17 electron counts, but it's not going to be stable. And so we'll see one of the things that we'll kind of be looking for is as we kind of talk about this electron counting, our goal is to help figure out like how stable is a compound likely to be. If it's octahedral, it wants to be 18. If it's tetrahedral, probably still wants to be 18. And if it's square planar, 16 is going to be kind of that magic number of where it actually wants to be. Now, that doesn't mean a compound can't exist at other electron counts. It's just not going to be as stable if it's not at those electron counts. And so here for tetrahedral, we also see some kind of general patterns here. So late first row metals prefer D10 configuration. So D10 would be like nickel 0 or like copper +1 or zinc +2. Those are transition metals that have 10 valence electrons basically on the metal. Those are going to be very stable for tetrahedral compounds because if you have 10 electrons on the metal, and again, you have 4 things coordinated to it that can each donate 2 electrons, that's a total of 18. And so we can actually, again, have kind of a sweet spot there for from a stability standpoint and filling orbitals. So first row metals, D10 configurations, pretty stable for tetrahedral. It's probably going to be almost impossible for tetrahedral systems to exceed 18 electrons. It's extremely, extremely rare. You'd have to have a kind of like a copper 0 tetrahedral or like a zinc 0 tetrahedral compound, which is just not likely. Like if they're making tetrahedral compounds, they're probably just going to get oxidized at that point and be 18 electron compounds. So never really going to go over 18, but we can have actually a lot of tetrahedral compounds with less than 18 electron counts. And this is actually almost kind of like mandatory for the early transition metals, right? If we're looking at like titanium or vanadium, molybdenum, some of those early transition metals, if you attach 4 things to them, you can get 8 electrons from the 4 things that are being attached. But those metals, even if they're a 0 oxidation state, only have like 4 or 5 electrons or something to start. Like there's no way to get up to 18. So early transition metals do often prefer tetrahedral versus octahedral. And they will be at these lower electron counts because there's kind of almost no way around it. Even though octahedral would give a higher electron count, it doesn't necessarily give it something that's more stable because those early transition metals, in terms of kind of bonding interactions, often are going to be a little bit weaker in terms of like covalent bonding to things. In terms, and I guess to give a quick perspective of that, electronegativity review of transition metals. Where are our most electronegative transition metals? Yeah, kind of the bottom right of the transition metals over by like palladium, platinum, and gold. Whereas like the upper left part of our transition metals, those early ones, they're actually pretty electropositive. They're kind of almost like group 2 metals in some instances in that regard. So if you are not very electronegative in terms of covalent bond strength that you have, it's going to be pretty weak. You're not going to really be sharing electrons very efficiently. And so the weaker your covalent bonding gets, like your delta gaps and everything always are going to shrink. And smaller delta gaps are going to typically favor tetrahedral compounds for a lot of things. So tetrahedral ends up kind of being the preference for a lot of those early transition metals. Even though they're not going to be 18 electron, tetrahedral ends up a little bit more preferable for a lot of them than octahedral for that reason. We'll still see chromium and molybdenum do a lot of octahedral things, but those first 3 columns of the D block, it's pretty rare to get anything that's not tetrahedral for a lot of them. That's kind of the common pattern that we usually see. All right, so let's actually get into how do we go about counting these electron totals for compounds. So there's 2 different methods for this. I'm going to talk about each. You can pick whichever one you kind of prefer. And in all honesty, there's not one that's like just better than the other. They're just different. And so it's kind of whatever perspective you prefer to look at for things. So there's what's called the donor pair method, which is what I would call really more of an ionic method. That's actually the one that I personally prefer. And then there's also a neutral ligand method, which this one in some ways can be easier because you don't have to worry about any oxidation states of things really off the start to count things. And other people prefer that, like my PhD advisor, for instance, preferred that method. It's just kind of everyone's just your personal preference for which of these you like better. So I'm going to go through each. For this first one, this donor pair method for counting electrons, we're always going to treat everything for this first method as an even number electron donor or a 2 electron donor for kind of just monodentate ligands. Ligands that coordinate with 1 atom, we're going to consider they're going to donate a pair of electrons, which means anything that normally doesn't have a pair of electrons to donate, like a halide, like chlorine, for example. Chlorine, if it's just neutral chlorine, really only has 1 electron to donate to something, right? If you imagine pairing with like hydrogen to make HCl, hydrogen has the other electron to make that covalent bond. So in order for it to be a 2 electron donor, you have to make it the halide or chloride in that case. So chlorine will be Cl minus as far as how we treat it in this ionic system, whereas the neutral setup will actually just count chlorine as a 1 electron donor instead because it doesn't have a full pair on its own. That'll be kind of like the difference kind of between them. So first one, the ionic version, anything that it doesn't have a full pair of electrons on its own to donate, we basically make it an anion to give it a pair so that it's a 2 electron donor in terms of how we count things. Now, as that happens, and this is the useful part of doing the ionic method, and the part of it that I actually like, is that it helps you figure out the oxidation state of the metal as you do that. Because if you have like kind of, example compounds that we've seen before, if you have the formula of the compound, you're like, oh, I have 3 chlorines, so I treat them each as -1, and everything else is neutral, the whole compound is neutral, it means my metal must be +3. You can find the oxidation state that way. So it's kind of, we use this ionic method already to find oxidation states. So in some ways, if that's how you're used to looking at things, like I think it kind of makes sense as far as how the electron counting of things work for that. But it does kind of require you to understand the oxidation state of the metal to fully count all of your electrons properly. And we'll go through examples of applying this in just a second. The neutral ligand version of this, kind of the things that change, we treat everything basically as neutral. That includes the metal, all of the ligands. And really, if we're kind of looking at this, that means that cyanide actually becomes just plain CN, which is kind of weird as we're going through stuff like that. So we treat everything as a neutral ligand. And if it doesn't have a full pair as a neutral ligand, then it's adding like 1 electron instead of 2 electrons to the count. And so we're going to see some applications of how we go about counting this, because I think that's going to be the easier part rather than just seeing kind of some of these descriptions. So let's take a look at some examples, and I think I'm going to actually switch my view for this, so I think it'll make more sense to switch. And there is actually a chart here. I'll come back to this in a second too. So I think the first example that those slides actually takes a look at is this one. Well, actually, it doesn't really matter. We can do some other variations. Let's do this, the first one. If I look at this compound, then I want to actually count electrons for this compound. So if I go through the ionic version, or method A that was kind of described in that slide, the way I would go through counting things is I'm going to look at the ligands here first. And I have 1 chloride and I have 5 carbonyls. So for chlorine to be a 2-electron donor, it is going to have to be Cl minus. So that means Cl minus will be a 2-electron donor. And I have 1 of them. For the carbonyls, it's already a 2-electron donor as a neutral ligand. So I don't have to change its charge. It's just a 2-electron donor already, and I have 5 of them. The chlorine part, so for the way this ionic method works, it treats everything as basically an even number electron donor. So for chlorine to be a 2-electron donor, it has to be a negative charge, right? Because otherwise, usually if it's just neutral chlorine's only got 1 electron to really donate and interact, it's going to keep its 3 lone pairs no matter what. And so for this to be a 2-electron donor, this has a negative charge. That's kind of how we're assigning that. That negative charge is going to matter for the metal, because in order for this method to work, we have to know the oxidation state of the metal, which if I'm looking at this compound, what's the oxidation state of the manganese? Yeah, it should be +1, right? Because carbonyl, CO, this is a 2-electron donor already if it's neutral, right? CO, we think like kind of like Lewis dot structure is this, and it's that pair of electrons in the carbon that's always donated to things. So it already had the 2 electrons to donate as neutral ligand. That's why I had no charge. That's why this ends up manganese +1, which means for electron counting purposes, we look at manganese. How many electrons does manganese +1 have? Yeah, it should have 6. So 6 electrons. All right, so now if I look to add all this up, I have 2 electrons, right? 10 from the chlorine, 10 electrons from the carbonyls, 6 electrons from the manganese. I have an 18-electron compound, which means that this is likely going to be stable. Right? It's an 18-electron, and I know it's octahedral because it's got 6 things attached to the metal. Right? So anything that's octahedral, 18 electrons, is going to be stable. Now, the other variation on this, as far as how we would count electrons, is we treat everything as neutral. So I'll call this covalent, or you can call it neutral, which is like the second method, or method B. The difference here is that chlorine is just going to be neutral chlorine, which is going to be a 1-electron donor. And then we have carbonyl, which as a neutral ligand is already a 2-electron donor, like we said. We still have 5 of those. And then for the manganese, we just treat it as manganese 0. It's just how many electrons the manganese itself has. So manganese in this case, neutral manganese has 7 electrons. And now if I add this total, right, 1 electron, 10 electrons, 7 electrons, the total is still 18. And the total should be the same regardless of which method we use. So the difference is, if you're doing kind of this neutral version, The nice part is you don't have to worry about the metal oxidation state. The awkward part is you're probably already used to thinking of chlorine as like Cl minus all the time, but you have to treat it as just neutral chlorine. And that does mean you get a lot of kind of like one electron donors for things that would normally be an anion if we're looking at charges. Which for me is why I usually prefer this method, because that's kind of what we're already used to some extent for looking at oxidation states of things, like going through naming and other things like that. So I kind of prefer the ionic method, but in all reality, it doesn't really make a difference. We can use either one. And something that can be useful, and you will have this for the quiz on Friday, so that we'll make this a little bit easier as well, is there's a list of ligands that I have up in kind of the notes I put up today. And I know this is small, so don't worry about trying to read it all here, but it has a list of basically all of these really common ligands for coordination compounds or even organometallic compounds. And it tells you how many electrons they're donating based on which method you're using to count, right? And so that will help. And you'll have this, like I said, available to you like on Friday and probably even next week for the exam, just to make that process easier. Because I'm not going to try to add a bunch of like extra memorization of things on top of that, although I think it is hopefully a lot of this you can probably figure out or guess without the chart, but the chart will be there to kind of help and make sure people hopefully have a good feel for what they're looking at. There are some definitely weird compounds, especially starting about halfway down. The rest of these are a lot of organometallic things or just organic compounds that maybe are things you're not familiar with. So having those to help count, I think will help with that as well. You will see for things like benzene or the 8-5 cyclopentadienyl ligand, like they are 6 electron donors, both if we're doing the ionic method. But the neutral method, benzene is neutral, so it stays a 6 electron donor because it has 6 pi electrons it can donate. But the cyclopentadienyl for the neutral method is only a 5 electron donor because it technically wouldn't be to protonate or have the negative charge for that extra electron. It's just the way the counting system kind of works. So let's do just a couple more examples, I think, of the counting. I think it's the easiest way to kind of get familiar with this and more comfortable with it. So let's see where's this one had. Okay, let's take a look at ferrocene then. So we'll take a look at ferrocene and I'll make up a couple more. So ferrocene is this compound. So this is the cyclopentadienyl ligand that I introduced earlier. It's 8-5. So in terms of electron counting here, and I typically just abbreviate CP as just the cyclopentadienyl ligand as CP. If I'm using, again, the ionic method for counting this, that basically means we're treating this as CP minus. So it is actually this with a negative charge for the ionic method. And in terms of the pi electrons it can donate, like benzene, it should have 6. So it's a 6 electron donor. And again, that would be in the chart that I just showed a second ago. You can look at as well. And if we have 2 of them, 6 electrons times 2. And then if I look at iron, if the cyclopentadiene has a negative charge and I have 2 of them, iron must be, have a 2+ charge, which means how many electrons is the iron going to have? Yeah, it should have 6 electrons after it has that +2 charge. So if I have 12 plus 6, that gives me 18 electrons, right? If I did the other kind of method, right, the covalent method for counting this or the neutral version, it treats CP as a neutral ligand. So it'd be 2 times, it's not 2, 5 electrons each. I have 2 of them, but now the iron is just iron 0, which instead of 6 electrons has 8 electrons. So 10 plus 8 is still 18. So it doesn't matter kind of which variety we choose. We should still get to the same total. Now, one thing I'll point out, this compound is extremely famous, very common. It's actually the first fully characterized organometallic compound. It was kind of revolutionary for understanding how these organic systems can interact with metals. Scientists really had no idea how these things combined and interacted until they got a crystal structure back in the 50s. It is the one I had. Yeah, it has the painting in my office. It is. You'll see it typically written or drawn probably like this. And it's referred to also as a sandwich complex because those 2 rings are actually kind of like in parallel with each other. And so you end up with a metal compound kind of just sandwiched between those 2 rings. There are other sandwich compounds that we can make with other metals, but they aren't very stable because Iron's the one that's 18 electrons. If I switch that iron for a manganese, or if I switched it for like a cobalt, it'd be like a 17 or a 19 electron compound. It's not going to be as stable. And in fact, when we're not stable, like manganese, it's 17 electrons. Usually when it's just less, that's when you'll see a lot of weird stuff happen where you'll start making like metal dimers, or in the case of manganese, it actually just makes a polymer with all of these rings where every manganese is attached to 3 rings, and those rings are also attached to other manganese, and it's just a whole mess of a system instead of like a single molecule. And that's when you get some other kind of different behaviors when you don't have those 18 electron counts. But we can make like cobaltocene and nicolocene and some of these others be like 19 or 20 electron compounds. However, they are, for the most part, explosive if they are in air or above about negative 30 degrees Celsius, which gives an indication about the stability. They're not very stable. Ferrocene, I could put ferrocene on this table and come back in 100 years and it would still be ferrocene just sitting there on the table. Like, it is incredibly robust and stable. And I think that shows the power of kind of this 18 electron rule in terms of kind of stability on most compounds. Like 18 electron is the sweet spot count for most compounds, especially octahedral things. When you have ring systems like this, one thing I will point out, if these are each 6 electron donors, that's almost like having 3 things in those spots. So if I have 3 here, 3 more there, that's kind of like having 6 things. It's kind of pseudo-octahedral, even though it's rings and not like individual ligands that are attached there. Is another way to kind of think about that coordination environment. Just to show one other kind of quick example, this is something else that's fairly common. You'll see a lot of compounds like this that have a metal with like a cyclopentadiene ring like that. And then you have a bunch of things below that are attached to the metal. If you ever see this geometry configuration, you will hear this referred to as a piano stool. Like geometry, that is pretty common. And probably in this case, exactly as it's drawn, it's probably not the most stable for iron. It would actually probably rather be manganese in that configuration. Mainly because now, oxidation state-wise, this iron is actually only iron +1 if these are all carbonyls. And so actually manganese would be better. That would be the 18 electron compound in that case. But let's do one more quick example of electron counting, and then I think we'll kind of wrap up for today. So let's do this compound. I think this is close to one of the ones that was on the homework, for instance. So if I'm looking at this compound, we'll start again with the ligands. Cyanide, what do we know about cyanide? If I'm doing this the ionic way, yeah, it is Cn minus to be a 2 electron donor. I have 1 of them. I have carbonyls, which neutral 2 electron donors. We have 3 of them. And then iridium, what's its oxidation state there? Not -1, but yeah, +1. So it's iridium +1. How many electrons would that be for the iridium? Careful. How many valence electrons total would it have? Yeah, it should be 8. But you count the S and the D for the neutral metal, and then if you're out, as you start to get a positive charge, you're taking them off. So in that case, it would have 9 valence electrons normally, like 7 in the D and 2 in the S. Taking 1 off leaves 8 total. So it's going to have 8 electrons that it contributes. So 2 electrons, 6 electrons, and 8 electrons. If I'm adding all these together, are 16. So is this compound stable? What is its geometry? Yeah, it's 4 coordinate, but if it's iridium, 3rd row transition metal, late transition metal, 16 electrons, this thing is stable because it's square planar. Yes. So when we're doing those counts and looking at kind of applying the electron counts to the stability, do look at the geometry of it. Right? 4 coordinate systems, if it's 16 electrons, it's probably square planar, and that will be stable for most of them. And so iridium +1 really likes to be 4 coordinate, square planar, almost always. There's like almost no exceptions to that for iridium +1 compounds. It will make octahedral compounds, but usually not as +1. It'll do it as +3, which will be the part we'll see start getting to probably a little bit either Friday or Monday when we talk about reactions. Right. Questions over, and I guess maybe before I do that, if I did the covalent route in terms of what changes, cyanide has to be treated as neutral. So instead of 2 electrons, it's 1 electron. Carbonyl is still the same. It's still 2 oops, wrote that in the wrong order. 2 electrons for each of them for all 3. And now instead of iridium plus 1, it's just plain iridium, which will have 9 electrons, which when I add up the total is still 16. Right? So again, either method and whatever is more comfortable. So Friday, the plan is to have our quiz Friday. Most of it's going to be similar to things you've seen probably homework-wise to date, with just a little bit of some of this electron counting kind of starting to work its way in that we've started to see today in those applications. So expect a little bit of naming, identifying kind of like if you have a compound, like what's its geometry likely to be? Is it high spin, low spin? Is it going to have Ion-Teller distortions? Is it going to be stable based on electron counts? Those are kind of the big focus of a lot of the stuff that we've done so far. And then Friday after that quiz, we'll probably start to talk a little bit about kind of some more reaction things again. We have talked about associative-dissociative mechanisms, but we'll also talk about for square planar compounds, specifically something called the trans effect. That'll probably be what we look at Friday. And then Monday, we'll get into looking at kind of just other reaction types for a lot of these compounds, which will be like oxidative addition and reductive elimination is kind of the big 2 that we'll spend some time on. And that'll probably get us pretty close to the end in terms of topics and things we'll kind of see this semester. So Friday quiz, Wednesday next week exam. For take-homes for things, I do want to actually ask people's preference about how I want to do these last ones. So the options are we can have separate take-homes for exam 3 and the final, where I can give the exam 3 one probably either like tomorrow or so and have it due probably towards the end of next week, and have a separate one for the take-home that'll probably do the end of finals week. Or I can lump them and have them as a single assignment, due probably the middle or so of finals week, which looks like there's a lot of nods no. You'd rather have 2 separate ones. Okay, we can do that. So question. It would still count. It would be like one thing that I would just post kind of together, do it one time, but it would have like part of it towards exam 3, part towards the final. Yeah, I'll do it separate. Well, I'll get that posted. I'll try to get it posted today before I leave, but at the latest tomorrow for the take home for exam 3. That way you can see kind of what things are on the take home, and that'll give you a little bit of an idea too, maybe what things to expect in class. I do think this last one is usually a little bit easier just because compared to some of the things we have been doing, the topics I think are easier. It's also just shorter. So it will probably be a slightly heavier in-class portion than take-home because of that for exam 3. And then exam 4 will be about a 50-50 split, or the final exam will be a 50-50 split of kind of take-home in class. So, yeah. Class reminder also, don't forget to turn in homework if you haven't already, either to me or to D2L. It's exam review week. It's exam review and kind of just reviewing like neutralization reaction stuff, questions in the report.
We're doing the electric one next.
Yes, correct.